Your AI strategy was supposed to protect your data, but in reality it's doing the opposite. Not because of bad intentions, because of the model behind it. Cloud AI requires cloud connectivity. Cloud connectivity means logging, retention, and legal compulsion you can't opt out of. Your SharePoint documents deserve better. Today, I will show you how to run Llama locally, connect it to your SharePoint libraries, and build a retrieval system that never touches the public internet. Sovereign intelligence, not sovereign cloud. Here's what most organizations miss. The moment you connect a cloud AI assistant to your SharePoint, your contracts, your HR files, your strategy documents, and your board memos enter a pipeline you don't control. They travel across network boundaries you didn't architect. They sit in log files you can't delete. And in many jurisdictions, they become subject to legal requests you can't refuse. Microsoft's own Work Trend Index tells us that roughly 3 out of 4 knowledge workers now use generative AI in some form. Nearly half of them started in just the last several months. That acceleration isn't a statistic, it's a signal. The signal says your organization's most sensitive content is now being queried through models that exist outside your perimeter, trained on data you didn't approve, and retained in ways you can't audit. The risk isn't that Microsoft will misuse your data. The risk is structural. When you send a prompt to a cloud LLM, that prompt carries context. That context carries document chunks. Those chunks carry proprietary information. And once that information leaves your network, it enters a legal and technical framework that's not yours. This isn't theoretical. Organizations in regulated industries already face hard blockers. Healthcare providers can't send patient records to external APIs under HIPAA. Financial institutions can't expose trading strategies to cross-border processing. Government bodies can't risk extraterritorial legal compulsion. The Cloud Act in the United States allows authorities to compel disclosure of data, even when it's stored in European data centers. Contracts don't eliminate that risk. They merely define who pays when it happens. So the question isn't whether AI is useful. The question is whether your current architecture respects the boundary between your data and the rest of the world. Most organizations assume it does. They assume that enterprise agreements, data processing addendums, and region selection checkboxes create a sufficient barrier. They don't. Those tools improve transparency. They don't create sovereignty. Sovereignty means you control the hardware, the network, the model, the logs, and the legal jurisdiction. Anything less is delegation dressed up as protection. And delegation fails the moment the delegated party faces a legal obligation you can't override. That's the hidden leak. It's not a bug. It's the architecture. Why sovereign cloud is not enough. You have probably heard that sovereign cloud is the answer. Microsoft offers it. Other providers offer it too. The promise is appealing. Your data stays in your region. Processing happens locally. Access controls are stricter. Transparency improves. But here's the problem. Sovereign cloud is still cloud. And cloud means a provider headquartered in a jurisdiction that can compel access to your data regardless of where the servers sit. Legal analysis from ActiveMind. Legal makes this explicit. As long as US laws like the Cloud Act remain in force, US-based companies can be compelled to transfer data to US authorities even when that data is physically stored in Europe. Microsoft has acknowledged this tension. Their sovereign cloud for Europe promises stricter controls in regional processing. It can't promise immunity from extraterritorial legal obligations because Microsoft is a US corporation subject to US law. This isn't a criticism of Microsoft. It's a statement about structure. No contractual assurance can override a statutory compulsion. No checkbox can change the jurisdiction of the parent company. And no amount of marketing language can turn a hosted service into an owned system. For many organizations, this distinction is academic. For others, it's a hard blocker. Public sector bodies, critical infrastructure operators, regulated industries, organizations subject to GDPR Article 44 restrictions on international transfers. These entities need data processing that's not merely resident in the right region, but legally and technically insulated from external access. GDPR requires that personal data be processed lawfully, fairly, and transparently. It requires appropriate technical and organizational measures. And when using third-party processors, controllers must ensure that processing agreements match with GDPR's protections, including restrictions on transfers to countries without adequate protection. The standard contractual clauses and adequacy decisions that underpin many cloud arrangements are being challenged, renegotiated, and in some cases invalidated. The legal environment is shifting. Building on assumptions that held in 2022 is a risk in 2026. So sovereign cloud is a step. It's not the destination. The destination is an architecture where your data never leaves your control in the first place, where the model runs on your hardware, where the retrieval index lives on your network, where the query logs stay inside your perimeter, where the legal framework is the one you chose, not the one your provider is subject to. That architecture exists. It's called air-gapped intelligence, and it's what we're building today. The air-gapped alternative. Air-gapped doesn't mean disconnected from everything. It means disconnected from the public internet for the parts that matter. Your SharePoint still connects to Microsoft 365 for collaboration. Your users still authenticate through Microsoft Entra ID. Your document lifecycle still follows the governance rules you already built, but the AI layer runs inside your perimeter. The LLM sits on your GPU server. The vector database sits on your local network. The query interface resolves to an internal IP. And when a user asks a question, the answer is generated without a single packet leaving your controlled environment. This is zero trust applied to AI. Palo Alto Networks defines zero trust architecture as assuming no user or system is inherently trustworthy and requiring continuous verification. For AI, this means the ingestion service authenticates against SharePoint using OAuth. The vector database enforces role-based access control at the collection level. The query interface checks permissions before returning results. And the LLM runtime is isolated from outbound connectivity entirely. NIST describes role-based access control as enforcing three basic rules: role assignment, role authorization, permission authorization. Users only exercise permissions consistent with their authorized roles. In our architecture, this applies at every layer. The ingestion service has a role that allows read access to specific SharePoint libraries. The vector database collections are tagged with the permission levels required to query them. The chat interface verifies the user's Entra ID group membership before constructing the prompt. The result isn't paranoia, it's precision. Every document chunk carries its source. Every answer carries its citation. Every query carries its audit trail. And none of it leaves your building. Let me walk you through what this looks like in practice. SharePoint holds your documents. A local ingestion service authenticates via Microsoft Entra ID, enumerates your libraries, and extracts the content. A chunking engine breaks documents into semantically meaningful pieces. A local embedding model converts those pieces into numerical vectors. A vector database stores and indexes those vectors. A local Llama instance waits for queries. And a simple web interface lets your team ask questions and get grounded, cited answers. That's the architecture. 7 layers, all local, all under your control. The ingestion service runs on a modest server. It needs CPU, memory, and network access to SharePoint. It doesn't need a GPU. The chunking engine runs alongside it. The embedding model needs a GPU for speed but can fall back to CPU for smaller batches. The vector database needs fast SSD storage and enough RAM to hold the HNSW index. The LLM runtime needs the biggest GPU you can afford. And the query interface needs minimal resources because it's just a web application orchestrating calls to the other layers. This modular resource allocation means you can start small. A single server with a mid-range GPU can run the entire stack for a pilot with 5,000 documents and 50 daily users. As you grow, you move components to dedicated hardware. The vector database gets its own server with fast disks. The LLM runtime gets a dedicated GPU workstation. The ingestion service scales horizontally by adding more workers. You don't need to buy enterprise hardware on day one. But before we build it, you need to understand why retrieval isn't optional. It's the difference between a useful system and an expensive hallucination machine. The RAG imperative. Large language models are pattern completion engines. They predict the next token based on statistical patterns learned from training data. They don't know your organization. They don't know your contracts. They don't know your procedures. And when you ask them a question about content they have never seen, they invent plausible sounding answers. That invention is called hallucination. It's not a rare bug. It's a fundamental property of how these models work. A full survey from RxSieve categorizes hallucination mitigation into prompt engineering, decoding constraints, training interventions, and retrieval-based methods. The conclusion is clear. For factual grounding in changing or proprietary content, retrieval is the most reliable approach. Retrieval Augmented Generation, or RAG, inserts a retrieval step between the user and the model. AWS describes it simply. User input retrieves relevant information from a new data source. The combined query and retrieved context pass to the LLM. The result is generated from authoritative data, not from statistical guessing. Immutar adds the enterprise security perspective. RAG converts external data into embeddings, stores them in a vector database, retrieves the most relevant chunks for a query, and integrates them into the prompt. At every step, security must be enforced. Storage tier, data tier, prompt tier. Microsoft's Azure Architecture Center agrees. RAG is the industry standard approach to using language models with proprietary data. Each step, from chunking and embedding to retrieval and evaluation, must be carefully designed and measured. Here's the pipeline in practical terms. Your SharePoint documents contain text. That text gets broken into chunks. Each chunk gets converted into a numerical vector that captures its semantic meaning. Those vectors get stored in a specialized database called a vector database. When a user asks a question, that question also gets converted into a vector. The database compares the question vector against all the document vectors and returns the closest matches. Those matches get inserted into the prompt sent to the LLM. The LLM now has both its general training and your specific documents as context. It generates an answer grounded in your actual content. This matters because fine-tuning isn't a substitute. When you fine-tune a model on internal documents, you bake specific information into the model weights. Updates become expensive. Privacy questions multiply because private data used in training can be memorized and inadvertently reproduced. A recent case study comparing RAG against fine-tuning finds that RAG offers better factual accuracy and maintainability, especially when the knowledge base changes frequently. Your SharePoint content changes daily. RAG reflects those changes immediately. Fine-tuning doesn't. There's a mistake almost everyone makes when chunking SharePoint documents. They use the same chunk size for everything: PDFs, Word docs, Excel sheets, PowerPoint decks. Each document type has a different structure. A uniform chunking strategy destroys retrieval accuracy because it breaks semantic boundaries in some documents and creates noise in others. I will show you exactly how to fix this later. For now, remember that retrieval isn't a bolt-on. It's the foundation of trustworthy enterprise AI. The architecture we're building doesn't send your documents to a model for training. It sends relevant chunks to a model for inference. The documents stay local, the embeddings stay local, the model stays local, and the answers cite their sources. That's RAG, that's the pattern. Now let us look at what we're retrieving from. SharePoint as the content backbone. SharePoint isn't just a file store, it's the governance backbone of your document ecosystem. Microsoft defines effective document management as specifying document types, templates, metadata, storage locations, access controls, workflows, and policies for auditing and retention. That's not a feature list. It's a description of how your organization already manages knowledge. When you build an AI layer on top of SharePoint, you're not starting from scratch. You're extending an existing system. SharePoint already knows who can see what. It already tracks versions. It already enforces retention policies through purview. It already logs access through audit trails. Any AI system that bypasses these controls creates shadow governance. And shadow governance is where data breaches happen. The planning process for SharePoint document management is itself structured. Organizations identify document management roles. They analyze usage patterns. They plan site collections and libraries. They design content types that capture metadata and workflows. They configure approval processes. And they set policies for auditing, retention, and records management. This isn't overhead. It's the reason SharePoint is trusted in regulated environments. For our architecture, these structures are both an asset and a constraint. They provide rich metadata that can inform chunking decisions. A contract in the legal library carries different weight than a draft in the marketing folder. They provide clear access boundaries. The AI should never surface content from a library the user can't access directly. And they impose obligations. If a document is under legal hold, the AI must respect that hold. If a retention policy deletes a document after 7 years, the AI must not preserve it indefinitely in a vector index. SharePoint exposes this content through multiple APIs. The traditional SharePoint REST API allows programmatic access to lists, libraries, and files. A PowerShell script can issue a GET request against a library using a URL like your SharePoint site plus the API endpoint for list items. Appropriate headers and credentials retrieve the items for processing. The newer Microsoft Graph API provides a unified endpoint for SharePoint, OneDrive, Teams, and Exchange. And the Microsoft 365 Copilot Search API, currently in preview, allows hybrid semantic and lexical search over work content using natural language queries. For our local RAG solution, these APIs provide the pipeline's ingress point. A service running inside your perimeter authenticates against SharePoint using OAuth 2.0 through Microsoft Entra ID. It enumerates libraries, it downloads documents, and it feeds them into the ingestion process without exposing content to external providers. This is critical. The ingestion service is the bridge between SharePoint and your local AI. It must authenticate securely. It must respect rate limits. It must handle versioning, and it must run inside your network. If you deploy the ingestion service in a cloud virtual machine, you have reintroduced the problem you're trying to solve. The authentication flow is standard Microsoft 365. Register an application in Entra ID. Granted application permissions for sites. Read all or delegated permissions scoped to specific libraries. Store the client secret or certificate in a local secret manager, not in code. Use the client credentials flow for background ingestion and the on behalf of flow if you want user-scoped queries that respect individual permissions. This isn't exotic, it's the same pattern you use for any Microsoft 365 integration. What changes is the destination. Instead of sending documents to a cloud AI service, you send them to a local chunking engine. Instead of calling a cloud embedding API, you call a local sentence transformer. Instead of storing vectors in a managed service, you store them in a local Qdrant or Weaviate instance. The APIs are the same, the network path is different. That's the foundation. SharePoint isn't just where your documents live, it's where your governance lives. And our architecture preserves that governance while adding intelligence. But here is where most people get stuck. They assume they need a cloud LLM to make this useful. They look at the local deployment path and worry that the model will be too small, too slow, or too dumb. That assumption is outdated. Local versus cloud LLMs. The real trade-offs. Cloud LLM APIs offer undeniable advantages. Lower operational overhead, automatic scaling, access to frontier models with hundreds of billions of parameters. You don't manage drivers, you don't manage quantization, you don't manage failover. You send a prompt, you get an answer. But those advantages come with trade-offs that many organizations can't accept. Every prompt leaves your network. Every response passes through infrastructure you don't control. Every token incurs a cost that scales with usage. And the best models aren't available for local deployment at all because their weights are proprietary. Local LLM deployments flip that equation. The operational burden shifts to your team. The scaling responsibility becomes yours, but the data control becomes absolute. The cost becomes predictable, and the model becomes yours to configure, update, and audit. AI Multiple's comparison of cloud versus local LLMs notes that cloud models are attractive for organizations that prefer managed services and rapid experimentation. Local models are more suitable when data security and sovereignty are critical and where organizations have or can invest in appropriate hardware. That's our scenario. We're not experimenting, we're building production infrastructure. The hardware requirements for local Llama deployment are major but increasingly accessible. Guidance for Llama 3 suggests targeting NVIDIA GPUs with at least 16 gigabytes of VRAM, 32 gigabytes of system RAM, and roughly 50 gigabytes of free disk space for models and dependencies. Larger models or fine-tuning workloads benefit from 64 gigabytes of RAM and more GPU memory. Community reports describe successful deployments on Linux distributions like Ubuntu by compiling inference engines like Llama, CPP with CUDA support combined with appropriate NVIDIA drivers. Llama simplifies this further. It's a cross-platform application for macOS, Windows, and Linux that downloads and runs models via a local API endpoint. You pull a model with a single command, you query it with a simple HTTP request to localhost. No container orchestration, no model conversion, no manual dependency management. For production use, you will want to run Llama on a dedicated GPU server rather than a laptop, but the abstraction is the same. A 2026 total cost of ownership analysis suggests that beyond certain usage thresholds, running open source models on dedicated GPU servers can become more cost-effective than paying per-token API fees despite high upfront hardware costs. The exact threshold depends on utilization, model size, energy costs, and operational expertise. But the directional insight is clear. If your organization will process thousands of queries daily across tens of thousands of documents, local deployment isn't a luxury, it's a financial optimization. Subjective experience comparisons between cloud and local models tend to emphasize that frontier cloud models still outperform smaller local ones on reasoning and nuance. But local models are increasingly acceptable for enterprise tasks when carefully selected and configured. The main phrase is carefully selected and configured. A badly chosen local model with poor prompting will disappoint. A well-chosen model with good RAG will surprise you. For our architecture, the model isn't doing everything. It's answering questions based on retrieved context. It doesn't need to know quantum physics. It needs to synthesize policy documents, contracts, and procedures into coherent responses. That's a narrower task than general reasoning. And local models handle it well. Meta now offers Llama 4 as its flagship family alongside the open-weight Llama 3 series. Deployment paths exist for both cloud and local scenarios. For our air-gapped architecture, we pull the open weights, quantize them for our hardware, and serve them through Llama or Llama, CPP. The license is permissive for commercial use. The weights are yours, the model is yours, and the answers stay yours. Once you have committed to local inference, the next decision is the vector database. And this is where many architects make their first real mistake. Vector databases and embeddings. Embeddings are the bridge between human language and machine search. A sentence transformer model takes a piece of text and converts it into a dense vector of floating point numbers. That vector captures semantic meaning. Sentences about similar topics produce vectors that are close together in high-dimensional space. Sentences about unrelated topics produce vectors that are far apart. This isn't keyword search. A keyword search for termination policy might miss a document titled Offboarding Procedures. An embedding search finds it because the semantic meaning is similar. The model understands that offboarding and termination are related concepts. It encodes that relationship into the geometry of the vector space. Sentence transformers come in many flavors. The all-mini LM L6v2 model is small, fast, and runs well on CPU. It produces 384 dimensional vectors. The BGE large N model is larger, slower, and more accurate. It produces 1024 dimensional vectors. For a local air-gapped deployment, you run the embedding model on the same GPU server as your LLM or on a separate CPU worker. The critical rule is that the embedding model must run locally. Don't call a cloud embedding API. Doing so would send your document chunks to an external service, defeating the entire purpose of the architecture. The vector database stores these embeddings and performs similarity search. When a user asks a question, the question gets embedded using the same model. The database compares this query vector against all stored document vectors and returns the nearest neighbors. This is called approximate nearest neighbor search, or ANN. It's fast even with millions of vectors because the database uses specialized index structures. Several vector databases are available. Quadrant is written in Rust. It's fast, memory efficient, and supports rich metadata filtering. You can attach tags to each vector, such as document source, library name, author, and permission level. Then you can filter searches to only vectors from libraries the user is allowed to access. Weaviate offers a GraphQL interface and native multimodal support. Milvus is designed for cloud-native scaling with Kubernetes. Chroma is lightweight and ideal for prototyping. For an air-gapped SharePoint deployment, Quadrant and Weaviate are the pragmatic choices. Both run on-premises via Docker. Both support the metadata filtering you need for permission-aware retrieval. Both have stable APIs and active communities. The choice between them often comes down to team preference. If your team likes REST APIs and JSON, qdrant feels natural. If your team likes GraphQL and semantic search features, Weaviate fits better. Chunking strategy determines whether your embeddings are meaningful or noisy. A document chunk is a piece of text that gets embedded as a single unit. If chunks are too large, they dilute meaning. A 5,000-word chunk about the entire employee handbook embeds into a single vector that represents everything and nothing. If chunks are too small, they fragment meaning. A single sentence like Section 4.2 applies to all full-time employees, carries no context about what Section 4.2 actually says. The mistake I mentioned earlier is using uniform chunking for all SharePoint document types. PDFs need page-aware boundaries because page breaks often separate unrelated topics. Word documents need heading-aware chunking because headings define semantic sections. Excel spreadsheets need row group chunking with header preservation because a row without column headers is meaningless. PowerPoint decks need slide-level chunking because each slide is a self-contained unit. Pinecone's research on chunking strategies confirms this. Fixed-size chunking with overlap works for homogeneous text. Semantic chunking based on sentence boundaries works for narrative documents. Recursive chunking that tries paragraphs, then sentences, then words works for mixed content. For SharePoint, you need a hybrid approach. Detect the document type, apply the appropriate strategy, preserve metadata at every step. The practical setup looks like this. Your ingestion service downloads a Word document from SharePoint. It extracts text while preserving heading structure. It breaks the text into chunks of roughly 500 tokens with a 50-token overlap. It attaches metadata to each chunk, including the source URL, document title, author, last modified date, and SharePoint library. It sends the chunk to your local sentence transformer. The transformer returns a vector. The vector gets stored in qdrant with its metadata. The process repeats for every document in the library. For a library of 1,000 documents, this takes minutes, not hours. For 10,000 documents, it takes longer but runs unattended. And once the initial index is built, Delta updates handle changes. When a document is modified in SharePoint, the ingestion service detects the change, rechunks the updated document, re-embeds the chunks, and updates the vectors in the database. Deleted documents trigger vector deletion. That's the memory layer. Now for the brain. The midpoint revelation. Everything we have covered so far is what vendors sell you. Cloud AI with enterprise controls, sovereign cloud with regional processing, managed RAG with vector databases. The environment is full of platforms that promise to solve this problem while keeping you inside their ecosystem. But the real architecture is simpler than you think. A single GPU server, an open source vector database, a local Llama instance, a lightweight web interface, and the SharePoint APIs you already know how to use. That's the entire stack. No cloud model subscriptions, no per token pricing, no vendor lock-in, no legal exposure. This isn't science fiction. In April 2025, a developer published a complete implementation of exactly this architecture for SharePoint on-premises. CPAT minimal API for the backend, qdrant for the vector database, Ollama for local LLM inference, SharePoint as the document source. It handled authentication, ingestion, chunking, embedding, retrieval, and generation, all on local hardware, all under local control. A Reddit discussion from August 2025 details a similar implementation scaling to over 6,000 SharePoint documents. The developer faced real problems. Chunking PDFs with mixed layouts, handling SharePoint rate limits, tuning retrieval to avoid surfacing outdated versions, and they solved them with open source tools and community support. The point isn't that these specific implementations are production ready for your environment. The point is that the architecture is proven. People are building this today. They're solving the problems. And they're doing it without sending proprietary data to external APIs. What changes isn't the technology, it's the stance. Most organizations approach AI as a service to consume. They evaluate vendors, they negotiate contracts, they audit compliance, and they hope the vendor's architecture matches with their risk model. The stance we're taking is different. We treat AI as infrastructure to own. We select open models with permissive licenses. We deploy them on hardware we control. We connect them to data sources we govern. And we accept the operational burden in exchange for sovereignty. That's the shift, from cloud first to sovereignty first, from consumption to ownership, from delegation to control. Let me show you exactly how the data flows. The ingestion layer. The ingestion service is the bridge between SharePoint and your local AI. It's also the most security-sensitive component because it has read access to your document libraries. Design it carefully. SharePoint content is unstructured, versioned, and permissioned. You can't simply dump files into a vector database and hope for the best. The ingestion service must understand document types, respect access controls, handle versioning, and manage Delta updates. If it fails at any of these, your AI layer becomes either inaccurate or insecure. The first decision is authentication. The ingestion service must authenticate against SharePoint Online or SharePoint on-premises using Microsoft Entra ID. For SharePoint Online, this means OAuth 2.0 with either application permissions or delegated permissions. Application permissions grant the service broad access, which is simpler but less secure. Delegated permissions scope access to what the specific user or service principal is allowed to see which is more secure but more complex to manage. For an air-gapped architecture, I recommend a hybrid approach. Use application permissions scoped to specific libraries rather than sites. Read all across the entire tenant. Create a dedicated service principal in Entra ID with a descriptive name like SP local rag ingestion. Grant it access only to the libraries you intend to index. Store the client's secret or certificate in a local secret manager like HashiCorp Vault or Azure Main Vault if you have a hybrid environment. Never hardcode credentials. Never commit secrets to repositories. The SharePoint REST API provides the ingestion endpoint. You construct URLs like your SharePoint site collection plus the API path for list items. You specify headers for JSON, accept, and content types. You handle pagination because libraries can contain thousands of documents. And you filter by content type, modified date, or library path to limit the scope. Microsoft Graph offers a more modern alternative. The Graph API provides a unified endpoint for SharePoint, OneDrive, Teams, and Exchange. For document ingestion, you query the Drive items endpoint for a specific site or library. You get metadata including file name, size, last modified date, and download URL. You download the file content using the download URL, and you process it locally. The Microsoft 365 Copilot Search API, currently in preview, offers a third option. It allows hybrid semantic and lexical search over work content using natural language queries. For our architecture, this is less relevant for ingestion, but useful for validation. You can compare your local RAG results against Copilot Search to verify coverage and accuracy during testing. Document extraction is where the ingestion service earns its keep. Different document types require different extractors. For Word documents, the docx format is a zip archive containing XML files. You can extract the text from document XML without installing Microsoft Office. For PDFs, you need a text extraction library. Be careful with mixed layout PDFs that contain both text and images. Tables in PDFs are notoriously difficult to extract correctly. For Excel spreadsheets, you need to flatten rows into text while preserving column headers. For PowerPoint decks, you extract text from slides and optionally speaker notes. The extraction step must preserve structure. A Word document with clear headings should produce text segments that know which heading they belong under. An Excel sheet should produce rows that include column context. A PowerPoint deck should separate slides. The structural metadata feeds into the chunking engine later. If you throw away structure during extraction, the chunking engine has nothing to work with. Let me give you a concrete example of what extraction looks like for a typical contract document. A Word file named Employment Contract Template. Docs lives in the HR library. The ingestion service downloads it using the SharePoint REST API. It opens the docx package, which is a zip archive containing XML files. It reads document.xml and extracts paragraphs while preserving the paragraph styles. Paragraphs styled as heading 1 become section markers. Paragraphs styled as normal become body text. Paragraphs styled as list bullet become list items. The extraction output is a structured text file that looks like this. Heading 1, Employment Terms. Body, this contract is governed by the laws of the state of Delaware. Heading 1, Compensation. Body, the employee shall receive a base salary as specified in Appendix A. This structure is exactly what the chunking engine needs to create semantically coherent chunks. PDF extraction is more complex because PDF is a presentation format, not a content format. A PDF file contains drawing commands, not paragraphs. The text you see on the page is positioned absolutely. Two words that appear next to each other might be stored in the PDF as separate objects with no explicit relationship. Good PDF extractors like PyPDF2, PDF Plumber, or PDF Miner use heuristics to reconstruct reading order. They detect columns, they identify headers and footers, they separate tables from body text, but they're not perfect. A scanned PDF that contains images instead of text requires OCR, which adds another layer of complexity and error. Tesseract is a common open source OCR engine. It converts images to text with reasonable accuracy for clean documents, but handwritten annotations, stamps, and poor scan quality will produce garbage text that pollutes your index. For Excel, the challenge is that a single spreadsheet might contain multiple sheets, each with a different purpose. Sheet 1 might be employee data, Sheet 2 might be salary bands, Sheet 3 might be a lookup table. If you flatten the entire workbook into a single text stream, the retrieval engine can't distinguish between an employee name and a salary band value. The extraction must preserve sheet boundaries. It must include column headers in every data row context, and it must skip empty rows and hidden sheets that contain no meaningful content. PowerPoint extraction faces the opposite problem of Excel. Each slide is already a self-contained unit, but slides contain title text, body bullets, speaker notes, and embedded charts. The title and bullets are usually the content you want to index. Speaker notes might contain presenter guidance that's irrelevant to document retrieval. Charts contain data that might be useful if extracted as text, but is usually stored as images. A good PowerPoint extractor pulls title and bullet text while optionally including speaker notes if your use case requires them. Error handling at the extraction layer is non-trivial. Documents in SharePoint aren't always well formed. A Word file might be corrupted, a PDF might be password protected, an Excel sheet might contain circular references that crash the parser. Your ingestion service must handle these gracefully. Log the failure, skip the document, alert the administrator, and continue with the rest. A single bad document shouldn't stop the indexing of 10,000 good ones. Retry logic with exponential backoff protects against transient failures. If SharePoint returns HTTP 500 or 503, wait 10 seconds and retry, then 20 seconds, then 40. If it still fails after 3 retries, log and move on. If the vector database is temporarily unreachable, queue the vectors in local storage and retry. If the embedding model is overloaded, pause the batch and wait for GPU memory to free up. Resilience isn't a feature you add later, it's a property you design in from the start. Delta handling is critical for production. You don't want to reindex 10,000 documents every night. You want to detect what changed and process only that. SharePoint provides a changes endpoint that returns items modified since a specific timestamp. Your ingestion service stores a watermark, the last processed timestamp, and queries for changes since that watermark. New documents get extracted, chunked, embedded, and stored. Modified documents get their old vectors deleted and new vectors inserted. Deleted documents trigger vector deletion. Security considerations at the ingestion layer are straightforward but non-negotiable. The ingestion service must run inside your perimeter. It should have no outbound internet connectivity except to Microsoft 365 if you're using SharePoint Online. It should log every document it processes, every error it encounters, and every API call it makes. Logs stay local. The service should fail closed. If authentication fails, it stops. If the vector database is unreachable, it stops. If a document can't be processed, it logs the error and continues with the rest. Rate limiting is a practical concern. SharePoint Online enforces throttling. If your ingestion service makes too many requests too quickly, SharePoint returns HTTP 429 and backs off. Your service must implement exponential backoff. Start with a modest request rate, increase it gradually, monitor for throttling responses, and schedule full reindexing during off-peak hours. The output of the ingestion layer is clean text with metadata. Document source, library name, author, last modified date, version number, permission level. This text and metadata feed into the chunking engine. And the chunking engine is where most implementations fail. Chunking and embedding strategy. Bad chunking destroys RAG. I want to be explicit about this because I have seen it happen repeatedly. An organization builds a beautiful ingestion pipeline, deploys an expensive GPU server, and configures a sleek chat interface. Then they ask a question and get an answer that's half right, half invented, and completely unsighted. The problem is almost never the model, it's the chunks. Chunking is the process of breaking extracted text into semantically meaningful pieces that can be embedded and retrieved individually. The goal is to create chunks that are self-contained enough to answer questions, but specific enough to avoid dilution. This is a tension. You can't satisfy both perfectly. You optimize for your document types and your query patterns. For Word documents, the best approach is heading-aware chunking. Pass the document structure, identify headings and subheadings, group paragraphs under their nearest heading. Each group becomes a chunk. If a group is too large, split it at natural boundaries like paragraph breaks. If a group is too small, merge it with the next group under the same heading. The result is chunks that carry semantic context. A chunk from the termination policy section includes the heading termination policy and the paragraphs beneath it. When a user asks about termination, the retrieval engine finds this chunk because the heading is embedded along with the content. For PDFs, the challenge is layout. A research paper has clear sections. A scanned contract doesn't. A brochure mixes text and images. The chunking strategy must detect the document structure. For structured PDFs, use section headers as chunk boundaries. For unstructured PDFs, use fixed-size chunking with overlap but include page numbers in the metadata so retrieval can cite sources accurately. For image-heavy PDFs, consider OCR if the documents contain critical text in images. But OCR adds complexity and error. Use it only when necessary. For Excel spreadsheets, chunk by row groups. Include column headers in every chunk. A chunk that says row 45, 5,000, approved, 2025-06-01 is meaningless without knowing that the columns are budget, status, and date. The chunk should read budget 5,000, status approved, date 2025-06-01. And it should include the sheet name and file name. If a spreadsheet has multiple sheets, each sheet becomes a separate chunking context. For PowerPoint decks, chunk at the slide level. Each slide is designed as a self-contained unit. Extract the slide title, the bullet points, and the speaker notes if available. Combine them into a single chunk per slide. If a slide is dense, split it into 2 chunks, but preserve the slide number in metadata so citations point back to the correct source. The chunk size depends on your embedding model and your LLM context window. A common starting point is 500 tokens per chunk with a 50-token overlap. The overlap ensures that sentences split across chunk boundaries appear in both chunks, reducing the chance that a critical connection gets lost. But this is a starting point, not a rule. If your documents are dense legal contracts with cross-references, you might need larger chunks. If they're FAQ documents with short answers, you might need smaller chunks. Let me walk you through what good chunking looks like for a specific document. Imagine a Word document titled Corporate Travel Policy, DocX. It has sections for booking, expense limits, approval workflow, and reimbursement. A heading-aware chunker passes the document structure. It creates a chunk for booking that contains the heading and all paragraphs under it. It creates a chunk for expense limits that contains the heading, the paragraph about daily limits, and the table showing per diem rates by city. It creates a chunk for approval workflow that contains the heading, the paragraph about manager approval, and the paragraph about executive approval for international travel. Each chunk is self-contained. A user asking about per diem rates in New York gets the expense limits chunk. A user asking who approves international travel gets the approval workflow chunk. The retrieval is precise because the chunk boundaries match with semantic boundaries. Now imagine the same document with bad chunking. A fixed-size chunker breaks the document every 500 tokens. The first chunk ends in the middle of the expense limits section. It contains half the daily limits paragraph and the beginning of the per diem table, but not the table headers. The second chunk starts with the rest of the per diem table, but not the section heading. When a user asks about per diem rates, neither chunk fully answers the question. The first chunk lacks the table headers. The second chunk lacks the context that this is about travel policy. The retrieval engine returns both chunks because they're topically related, but the LLM can't synthesize a coherent answer because the information is fragmented. This is how bad chunking destroys RAG accuracy silently. For Excel spreadsheets, chunking must preserve row relationships. Consider an employee directory with columns for name, department, manager, office location, and start date. A naive chunker might create chunks of 5 rows each. Row 1 through 5 get one chunk, row 6 through 10 get another. But if a user asks who manages the engineering team, the relevant rows might be scattered across multiple chunks. A better approach is to chunk by department group. All engineering rows become one chunk, all sales rows become another. This way, a query about engineering managers retrieves a single coherent chunk containing all engineering employees and their managers. For PowerPoint decks, slide-level chunking is usually correct, but some slides are dense. A quarterly review slide might contain 6 bullet points with detailed metrics. If you put the entire slide into one chunk, the embedding might dilute because the vector must represent 6 different ideas. In this case, split the slide into 2 chunks. The first chunk contains the first 3 bullets. The second contains the last 3. Both chunks carry the same slide title in their metadata, so the retrieval engine knows they came from the same source. Metadata preservation during chunking is critical. Every chunk must carry its source document URL, its position in the document, its heading hierarchy, its document type, its library name, its author, its last modified date, and its permission level. This metadata doesn't get embedded. It gets stored as payload data alongside the vector in the database. During retrieval, the metadata is returned with the vector. During answer generation, the metadata becomes the citation. Without metadata, an answer is unverifiable. And an unverifiable answer is worthless in an enterprise context. The embedding model converts each chunk into a vector. As I mentioned earlier, run this model locally. Popular choices include All Mini LM L6 V2 for speed and BGE Large N for accuracy. Both are available through Hugging Face and run on local hardware. The All Mini LM model is 384 dimensions. The BGE Large model is 1024 dimensions. Higher dimensions capture more nuance but require more storage and more compute during search. For most SharePoint deployments, All Mini LM is sufficient. If retrieval accuracy is critical and your document base is under 10,000 chunks, BGE Large is worth the overhead. The embedding step is batched for efficiency. Send multiple chunks to the model at once, rather than one by one. Modern embedding models handle batches of 32 or 64 chunks in parallel. This reduces GPU idle time and speeds up indexing. A batch of 1,000 chunks might take a few seconds on a modern GPU. A batch of 10,000 might take a minute. Schedule this during maintenance windows if your document base is large. Metadata preservation is as important as the chunk itself. Every vector in your database must carry metadata that answers 3 critical questions about its origin, its currency, and its access restrictions. The source URL lets the query interface cite the document. The last modified date helps the ingestion service detect staleness. The permission level enables filtered retrieval, so users only see content they're authorized to access. LangChain and Llama Index provide document loaders and chunking utilities that handle many of these concerns. LangChain's recursive character text splitter tries splitting on paragraphs, then sentences, then words. It's a good default for mixed content. Llama Index provides node parsers that preserve hierarchical structure. Both integrate with SharePoint through custom loaders or the SharePoint REST API. You don't need to write chunking logic from scratch, but you do need to configure it correctly for your document types. Once chunked and embedded, everything lands in the vector database. And the vector database configuration determines whether your retrieval is fast, accurate, and secure. Vector database configuration. The vector database is your AI's long-term memory. It must handle real-time updates, permission-aware filtering, and high query throughput. A bad configuration here means slow searches, inaccurate results, or unauthorized data exposure. These aren't hypothetical risks, they're configuration mistakes that happen in production. Qdrant is my recommended starting point for air-gapped SharePoint deployments. It's written in Rust, it's fast. It supports rich metadata filtering. and it runs on premises via a single Docker container. You can start a qdrant instance with a docker run command pointing to a local data directory. It exposes a REST API on port 6333, and it stores collections of vectors with attached payload metadata. A collection in qdrant is like a table in a relational database. You create one collection for your SharePoint index. You define the vector size, 384 for all mini-lem or 1024 for BGE large. You configure the distance metric, cosine similarity is standard for text embeddings, and you set up the index type. HNSW, which stands for Hierarchical Navigable Small World, is the default index type for approximate nearest neighbor search. It builds a graph structure where each vector connects to its nearest neighbors. Search traverses this graph to find close matches without comparing the query against every vector in the database. This makes search fast even with millions of vectors. Two parameters control the speed-accuracy trade-off. EF construction determines how thoroughly the graph is built during indexing. Higher values produce better graphs but slower indexing. EF determines how thoroughly the graph is searched during query time. Higher values produce more accurate results but slower queries. For initial setup, use EF construction of 128 and EF of 64. Tune these based on your observed query latency and retrieval accuracy. Metadata filtering is where qdrant shines for our use case. When you insert a vector, you attach a JSON payload. That payload might look like this: source URL pointing to the SharePoint document, library name like legal or HR, author email, last modified timestamp, and permission level like executive or standard. At query time, you can filter the search to only vectors where permission level equals standard or lower. This prevents the retrieval engine from finding chunks the user can't access. We-V8 is a strong alternative. It offers a GraphQL interface, native multimodal support, and built-in vectorization if you want to delegate embedding to the database. For our architecture, we keep embedding separate because we want control over the embedding model and batching, but We-V8's GraphQL interface is elegant for complex filtered queries. If your team prefers GraphQL over REST, We-V8 is worth evaluating. Milvus is designed for cloud-native scaling. It runs on Kubernetes. It supports billion-scale vector search, and it has a sophisticated architecture with separated storage and compute. For a single-tenant air-gapped deployment, Milvus is overkill unless you expect tens of millions of vectors. If you do, it's the right choice. But most SharePoint deployments don't reach that scale. Chroma is the lightweight option. It stores vectors in SQLite by default. It requires no server setup. And it's ideal for prototyping. But for production with multiple users, concurrent queries, and permission filtering, Chroma lacks the strongness of qdrant or We-V8. Use it to validate your pipeline. Then migrate to qdrant for production. Real-time synchronization between SharePoint and the vector database is a workflow problem, not a database problem. Your ingestion service detects changes in SharePoint. It extracts modified documents. It re-chunks and re-embeds them. It updates the vectors in qdrant, and it deletes vectors for removed documents. qdrant supports point updates and deletes by ID. You store the vector ID as a hash of the document URL and chunk index. When a document changes, you know exactly which vectors to replace. Query latency is your user experience metric. A user asks a question. The query interface embeds it. The vector database searches. The top matches get sent to the LLM. The LLM generates an answer. The total time from question to answer should be under 5 seconds for a good experience. Vector search itself should take under 100 milliseconds. If it takes longer, increase EF or add query replicas. If accuracy is poor, increase EF or rebuild the index with higher EF construction. Metadata filtering examples show why qdrant is powerful for our use case. A user asks about remote work policies. The query interface constructs a search with two conditions. The vector must be semantically close to the question, and the payload must have library equal to HR or legal and permission tier less than or equal to the user's tier. qdrant evaluates both conditions simultaneously. It searches only vectors that match the filter, then ranks them by vector similarity. This is far more efficient than retrieving all vectors and filtering afterward. Another filtering pattern is date-based exclusion. A user asks about the current vacation policy. The query interface adds a filter for last modified date greater than January 1st, 2025. This excludes outdated policy documents from 2023 or 2024. The answer reflects the current rules, not superseded ones. This pattern requires your ingestion service to keep the last modified date accurate in the metadata. If the date is wrong, the filter excludes the wrong documents. Monitor the database. Track query latency, index size, memory usage, and error rates. qdrant exposes Prometheus metrics. Scrape them with your local monitoring stack. Alert on anomalies. A vector database that silently degrades will produce poor answers without anyone noticing. Backup and recovery for the vector database is often overlooked. qdrant stores data in a local directory that you mount as a Docker volume. Backup this directory using your standard backup infrastructure. Snapshot before major changes like re-indexing or collection rebuilds. Test your restore procedure quarterly. A corrupted vector index with no backup means re-indexing your entire document base from scratch. For a 10,000 document library, that might take hours. For a 100,000 document library, it might take days. Capacity planning starts with sizing. A single vector of 384 dimensions at single precision takes roughly 1.5 kilobytes of storage. A million vectors take roughly 1.5 gigabytes. Add payload metadata and index overhead, and the total might be 3 to 5 gigabytes per million vectors. For a typical enterprise with 50,000 SharePoint documents chunked into 200,000 vectors, your database needs roughly 1 terabyte of fast SSD storage. Not massive, but not trivial either. Plan for 3 to 5 years of growth. Memory sizing is equally important. Qdrant keeps the HNSW index in memory for fast search. The index size depends on vector count, dimensions, and graph connectivity. A million vectors of 384 dimensions with HNSW might consume 2 to 4 gigabytes of RAM. Add the OS, the container overhead, and headroom for concurrent queries. A server with 16 gigabytes of RAM is comfortable for most deployments. 32 gigabytes provides room to grow. That's the memory layer. Now for the brain. The local llama runtime. The LLM is the reasoning engine. It takes the user's question and the retrieved document chunks and synthesizes a coherent answer. But it must run entirely inside your perimeter with no cloud dependency. Every byte of the model weight sits on your local disk. Every inference runs on your local GPU. And every response leaves through your local network. Ollama is the simplest way to achieve this. It's a cross-platform runtime for Llama and other open models. You install it on your GPU server. You pull a model with a command like Ollama pull llama 3, and you get a local REST API at localhost port 11434. Query it with a simple HTTP post. Send the model name, the system prompt, the user message, and the retrieved context. Get back a streaming response. The system prompt is critical for SharePoint RAG. It tells the model what its role is, what the context format is, and what constraints to follow. A good system prompt for this architecture looks like this. You're a knowledgeable assistant that answers questions based on the provided document context. Use only the information in the context to answer. If the context doesn't contain the answer, say you don't know. Cite the source document for every claim you make. Don't speculate, don't use outside knowledge. This prompt enforces 3 behaviors. Grounding, the model must use the retrieved context. Honesty, the model must admit when the answer isn't in the context. Citations, the model must reference sources. These constraints reduce hallucination and increase trust. They don't eliminate hallucination entirely. No prompt does, but they push the model toward the behavior you want. Temperature controls randomness. A low temperature like 0.1 or 0.2 makes the model deterministic and conservative. It sticks closely to the retrieved text. A high temperature like 0.7 makes the model creative and exploratory. For factual retrieval from SharePoint documents, keep temperature low. You want accurate synthesis, not creative writing. For brainstorming or summarization tasks, you might raise temperature slightly. But the default for most enterprise queries should be low. Quantization reduces model size and memory usage at a small cost in quality. Models are originally stored as 16-bit floating point numbers. Quantization converts them to 8-bit, 4-bit, or even lower precision. Q4KM is a common quantization format that balances quality and size. A 70 billion parameter model quantized to Q4KM fits in roughly 40 gigabytes of disk space and loads into roughly 40 gigabytes of VRAM. That's manageable on a single NVIDIA A100 with 80 gigabytes of VRAM or on dual RTX 4090 cards with 24 gigabytes each. For smaller deployments, consider the Llama 3.38 billion parameter model. It quantizes to under 5 gigabytes. It runs on a single RTX 4090 with room to spare. And with good RAG, it answers most enterprise questions adequately. It won't write poetry as well as the 70 billion model, but it will tell you what your vacation policy says. And that's the job. Llama 4 is now available from Meta as their flagship family. Deployment paths exist for both cloud and local scenarios. For our air-gapped architecture, you pull the open weights, quantize them for your hardware, and serve them through Ollama. Expect higher hardware requirements than Llama 3. Plan for an A100 or newer if you want the largest Llama 4 variant unquantized. For quantized deployment, a dual GPU setup or a single high memory card should suffice. The exact requirements will depend on the specific variant and quantization level you choose. Performance tuning for local inference involves several knobs. Context window size determines how much text the model can process in one call. With RAG, your context window must fit the system prompt, the retrieved chunks, and the user question. 5 retrieved chunks of 500 tokens each is 2500 tokens, plus the system prompt, plus the user question, plus the response. A 4000 token context window is tight. An 8000 token window is comfortable. A 16,000 token window is generous. Larger context windows require more VRAM. Balance this against your hardware. Batching at the LLM level is different from batching at the embedding level. LLM inference is harder to batch because each user query is independent and latency sensitive. For a chat interface serving 10 concurrent users, you might run a small batch of 2 to 4 requests if your GPU supports it. But most local deployments process queries sequentially or with minimal batching. The throughput is lower than cloud APIs. The latency is acceptable for interactive use. GPU utilization is your infrastructure metric. A GPU sitting at 10% utilization is wasted money. A GPU at 90% utilization is near capacity. Monitor utilization during peak hours. If you consistently hit 80% or higher, add a second GPU or upgrade. If you sit at 20%, you have headroom for a larger model or more users. Let me talk about context window sizing in more detail, because this is where many local deployments fail silently. You retrieve 5 chunks of 500 tokens each. That's 2,500 tokens of context. Your system prompt is 200 tokens. Your user question is 50 tokens. The model needs a few hundred tokens to generate the answer. Total context is roughly 3,000 tokens. If your model has a 4,000 token context window, this fits, but it leaves no room for longer documents or more retrieved chunks. If you want to retrieve 10 chunks or process longer contracts, you need an 8,000 token window or larger. Larger context windows require more VRAM. The KV cache, which stores the main and value matrices for each token during attention computation, grows linearly with context length. A model with 70 billion parameters and a 4,000 token context might need 30 gigabytes of VRAM. The same model with a 16,000 token context might need 45 gigabytes. This is why hardware planning must account for your expected context size, not just the model weights. Quantization affects context window capacity. A Q4 quantized model uses 4 bits per weight instead of 16. This reduces VRAM usage by roughly half for the weights. But the KV cache isn't quantized by default, it remains in full precision. So even with aggressive quantization, the context window is still the limiting factor for memory. Some advanced inference engines now support KV cache quantization, which can reduce memory further. But this is bleeding edge and may affect accuracy. Test thoroughly before deploying. For production, I recommend starting with an 8,000 token context window. It provides enough room for 5 to 7 chunks of 500 tokens each, plus system prompt and user question. If your documents are unusually long or your queries require cross-document synthesis, increase to 16,000. But don't increase beyond what your hardware can serve with acceptable latency. The LLM runtime is the crown jewel of your architecture. It's also the most resource-hungry. Plan your hardware around it. Everything else, the ingestion service, the chunking engine, the vector database, the embedding model, can run on CPU or shared GPU resources. The LLM needs dedicated VRAM and fast memory bandwidth. Don't under-provision it. Now for the interface that brings it all together. The query interface. A local brain without a face is just an API endpoint. Your team members need to ask questions in natural language and get grounded, cited answers without technical friction. The query interface is where sovereignty meets usability. Build a minimalist web interface. It doesn't need to be elaborate. A text input, a submit button, a response area, and citation links authenticate users through Microsoft Entra ID using the same credentials they use for SharePoint. This provides single sign-on and ensures that user identity is known for permission filtering. The query flow is straightforward. The user types a question. The interface sends the question to your local embedding model. The embedding model returns a vector. The interface queries quadrant with that vector, filtered by the user's permission level. Quadrant returns the top 5 most relevant chunks. The interface constructs a prompt containing the system instructions, the retrieved chunks, and the user question. It sends this prompt to Ollama. Ollama generates a response. The interface displays the response alongside citations linking back to the specific SharePoint documents. Citations aren't optional. They're the mechanism by which users verify answers and auditors trace decisions. Every answer must show the source document name, the library name, and the last modified date. Ideally, the citation is a clickable link to the SharePoint document. If the document is in SharePoint Online, the link opens in the browser. If it's on-premises, the link opens in the local SharePoint interface. The user can verify that the answer matches the source. Permission enforcement happens at 2 points. First, the vector database filters by permission level during retrieval. If a chunk requires executive access and the user is standard, quadrant doesn't return it. Second, the query interface should verify the user's group membership before constructing the prompt. This is defense in depth. Even if the vector database misconfigured and returned an unauthorized chunk, the interface would discard it. Immutar's guidance on securing RAG systems emphasizes this 3-layer security model. The storage tier is SharePoint with its native access controls. The data tier is the vector database with metadata filtering. The prompt tier is the query interface with user authentication and output validation. At each layer, organizations must enforce changing access controls, monitor and audit queries, and validate outputs to avoid both data leakage and hallucinations. Output validation is worth mentioning. The LLM can still hallucinate even with perfect retrieval. It might misinterpret a chunk, synthesize 2 unrelated chunks into a false connection, or ignore the system prompt and speculate. The query interface should implement basic sanity checks. If the answer contains unsupported phrases like "I think" or "it seems," flag it. If the answer contradicts a retrieved chunk, flag it. These checks aren't foolproof, but they catch obvious errors. The interface should also log every query, every retrieval result, every generated answer, and every user action. Logs stay local, they're your audit trail. If a user claims the AI gave them bad advice, you can reconstruct exactly what chunks were retrieved and what prompt was sent. This is governance, and governance is what makes a demo into a production system. Microsoft 365 Copilot Search API, currently in preview, offers a useful benchmark. It performs hybrid semantic and lexical search over work content and returns relevant documents. You can compare your local RAG results against Copilot Search to evaluate coverage. If your RAG finds documents that Copilot misses, you have an advantage. If Copilot finds documents your RAG misses, you have a tuning problem. Use this comparison during development. Disable it in production because it calls a cloud API. The query interface is where users experience the architecture. If it's slow, they won't use it. If it's inaccurate, they won't trust it. If it's ugly, they will tolerate it if the answers are good. Focus on latency and accuracy first, polish the interface later. Let me describe what a good query interface looks like in practice. The user opens an internal web page. They see a simple text box with placeholder text like ask about our policies, procedures, or documentation. They type a question. What is the procedure for requesting remote work? They hit enter. Within 2 seconds, they see a loading indicator. Within 5 seconds, they see an answer. The answer isn't a wall of text, it's a short paragraph. Remote work requests must be submitted through the HR portal at least 10 business days in advance. Your manager must approve the request. If approved for more than 3 consecutive days, the request requires director-level sign-off. Below the answer are citations. Source, Remote Work Policy. DocX, HR Library, last modified March 15, 2026. Source, Manager Handbook DocX, Leadership Library, last modified January 8, 2026. The user can click any citation to open the source document in SharePoint. This is the user experience that makes adoption happen. It's fast, it's grounded, it's verifiable, and it respects the user's existing SharePoint permissions. If the user doesn't have access to the leadership library, the manager handbook citation doesn't appear. The answer is still useful because the remote work policy chunk contains enough information, but the user can't access material they're not authorized to see. Error handling in the query interface must be graceful. If the vector database is down, show a message like, "The knowledge base is temporarily unavailable. Please try again in a few minutes." Don't expose stack traces. Don't expose internal service names. Don't expose the fact that you're running Qdrant on a server named GPU Server 01. These details help attackers and confuse users. If the LLM runtime is overloaded, implement a queue. The user submits a question, the interface shows position in queue. When the GPU is free, the query processes. For most organizations, this queue is rarely needed because local GPU inference is fast enough for interactive use. But if you have 100 concurrent users, queuing prevents the system from crashing. If the LLM generates an answer that fails validation, for example, it contains speculative language unsupported by the context, flag it for review. Show the user the answer with a disclaimer. This answer may contain information not found in the source documents. Please verify before acting. This isn't ideal, but it's better than presenting hallucinations as facts. The query interface should also support feedback. Thumbs up, thumbs down. A text box for explaining why the answer was wrong. This feedback feeds into your evaluation pipeline. You review thumbs down responses weekly. You identify common failure modes, bad chunking, missing documents, hallucinated citations, and you fix them. This feedback loop is how the system improves over time without retraining models. But here is what most proof of concepts ignore. They build a working pipeline, they demonstrate a good answer, and they declare victory. The real work starts after that. Permission tiers and access control. SharePoint already has role-based access control. Your AI must mirror it exactly, not approximately, not eventually, exactly. Every library has permissions. Every document inherits or overrides them. Every user has an effective permission level determined by their group membership, direct grants, and denied permissions. Your vector database must respect the same matrix. The naive approach is to build a single vector index for the entire organization and filter at the application layer. This fails. It fails because application layer filters can be bypassed by bugs. It fails because a single compromised query interface exposes the entire index. And it fails because it doesn't scale to fine-grained permissions like document-level access control. The correct approach is to tag every vector with its required permission level at ingestion time. When the ingestion service processes a document from SharePoint, it queries the SharePoint API for the document's effective permissions. It maps those permissions to a permission tier, executive, manager, standard, public, or whatever taxonomy your organization uses. It stores that tier in the vector's metadata payload. At query time, the user's permission tier is determined by their Microsoft Entra ID group membership. The query interface passes this tier to Qdrant as a filter condition. Qdrant only searches vectors where the permission tier is less than or equal to the user's tier. A standard user searching for budget information doesn't see executive budget documents. A manager searching for HR policies sees manager-level policies, but not executive compensation details. NIST defines role-based access control as enforcing 3 rules. Role assignment, every user must be assigned a role. Role authorization, every role must be authorized for the user. Permission authorization, every permission must be authorized for the role. In our architecture, role assignment happens in Entra ID. Role authorization happens when the query interface resolves the user's groups to permission tiers. Permission authorization happens when QDRANT filters by tier during vector search. This isn't a new concept. It's RBAC applied to vector databases. The novelty is that most RAG implementations ignore it. They build a single collection. They search everything, and they hope the LLM doesn't say something sensitive. That's not security, that's wishful thinking. Microsoft Purview Data Loss Prevention provides an additional layer. DLP policies in SharePoint can block documents from leaving the organization, but in our architecture, documents never leave. They're read by the ingestion service inside the perimeter and converted into vectors that also stay inside. DLP policies should still monitor the ingestion service's API calls to ensure it doesn't accidentally forward content to external endpoints. This is belt and suspenders. The architecture prevents leakage by design. DLP detects leakage if the design fails. Audit logging is needed for compliance. Every query must be logged with the user identity, timestamp, query text, retrieved chunks, generated answer, and citation list. These logs prove that the system is behaving correctly. They support investigations if a user claims they received an unauthorized answer, and they demonstrate compliance to auditors. Logs should be stored locally, not in a cloud logging service, not in a shared SaaS platform. In a local log aggregation system, like the Elastic Stack or Grafana Loki, retain them according to your organization's retention policy, secure them with the same RBAC that governs the rest of the system, and review them periodically for anomalies. Permission synchronization is an operational challenge. SharePoint permissions change. Users move between departments. Groups are reorganized. Documents are reclassified. Your vector database must reflect these changes. The ingestion service should periodically rescan document permissions and update vector metadata. The query interface should refresh user group membership on every login or at least every session, and you should run a full permission audit quarterly to catch drift. If a document's permission level increases, meaning fewer users should see it, the ingestion service must update the vector metadata immediately. If a document's permission level decreases, meaning more users should see it, the update can be batched. The risk of temporarily withholding accessible information is lower than the risk of temporarily exposing restricted information. This is governance. It's not glamorous, but it's what separates a proof of concept from a system your legal team will approve. Let me give you a specific example of permission mapping in practice. Your SharePoint tenant has 3 libraries. The public library contains employee handbooks and IT guidelines. The manager library contains team budgets and hiring procedures. The executive library contains board minutes and M&A strategy. In Entra ID, you have 3 groups. All employees contains every user. Managers contains users with direct reports. Executives contains the C-suite and VPs. The ingestion service tags every vector from the public library with permission tier standard, every vector from the manager library with permission tier manager, every vector from the executive library with permission tier executive. When a user in the all employees group queries the system, the query interface resolves their tier as standard. QDRANT filters the search to vectors with tier standard. The user sees employee handbook answers but not budget details. When a user in the managers group queries, their tier resolves as manager. QDRANT searches vectors with tier standard or manager. They see handbooks and hiring procedures. When an executive queries, QDRANT searches all tiers. They see everything. This is simple, auditable, and matched with SharePoint's native permissions. Edge cases exist. Consider a user who moves from engineering to sales. Their Entra ID group membership changes. The query interface picks up the new groups on next login. But if they had access to sensitive engineering documents yesterday and shouldn't see them today, the query interface must refresh group membership every session, not just at login. And it should cache group membership for no more than 1 hour to balance security against performance. Consider a document with custom permissions, a single file in the public library that's restricted to the legal team. The ingestion service must detect this exception. It queries the SharePoint API for the document's effective permissions. It sees that only the legal group has access. It tags the vector with permission tier legal instead of standard. This requires the ingestion service to check permissions per document, not just per library. It's slower, but it's accurate. And accuracy is the point. Consider inherited permissions that break. A library inherits from the site. A document inherits from the library. Then someone breaks inheritance on the document and grants access to an individual user. Your ingestion service must detect the broken inheritance and map it correctly. This is complex, but SharePoint's API returns effective permissions that account for inheritance breaks. Trust the API, map the result, and audit periodically. Permission drift is the silent killer of secure RAG. A document moves from the manager library to the public library. The ingestion service detects the move. It updates the vector metadata. But if the service is down during the move, the vector retains its old permission tag. A standard user might see manager-level content. To prevent this, run a full permission reconciliation weekly. Rescan all vectors, compare their permission tags against current SharePoint permissions, flag mismatches, and fix them. But the document base never stays small. Scaling and performance tuning. A few hundred documents is trivial. 10,000 documents with daily updates is a different problem. The architecture scales, but only if you tune it. Untuned systems degrade gracefully at first, and then suddenly, query latency creeps up. Embedding throughput drops, GPU memory fills, and users start complaining that the AI is slow. GPU batching for embedding generation is your first optimization. Embedding models process chunks in parallel. A batch of 64 chunks isn't 64 times slower than a batch of 1. It's perhaps 10 times slower. Batching amortizes the overhead of loading the model and transferring data to GPU memory. Use the largest batch size that fits in your GPU memory. For all mini-LM on a 24GB GPU, you can batch thousands of chunks. For BGE large, the batch size is smaller. Experiment and measure. Incremental delta indexing replaces full re-indexing. After the initial index is built, you only process changed documents. SharePoint's changes API returns modified items since a timestamp. Your ingestion service stores a watermark and processes only the delta. This keeps indexing time proportional to change volume, not total volume. A 10,000 document library with 50 daily changes takes minutes to update, not hours. Multi-collection sharding by department or document type reduces index size per collection. Qdrant searches a single collection in parallel across segments. But if a collection grows too large, search slows. Splitting into smaller collections, one per department or one per major library, keeps each collection fast. The query interface routes the search to the appropriate collection based on the user's query context. Or it searches multiple collections in parallel and merges the results. Caching frequent queries reduces redundant work. Some questions get asked repeatedly. What is our vacation policy? How do I submit an expense report? Cache the query vector, the retrieved chunks, and the generated answer. Serve the cached answer for identical or near-identical queries. Invalidate the cache when the source documents change. This can eliminate 50% or more of LLM calls for FAQ-style queries. Monitor vector DB query latency. Qdrant exposes Prometheus metrics, track P50, P95, and P99 latency. If P95 exceeds 200 milliseconds, investigate. Increase EF. Rebuild the index with higher EF construction. Add query replicas, or shard the collection. If P99 spikes, you may have a hot shard where one segment is overloaded. Qdrant can rebalance segments automatically, but you should verify it's doing so. For embedding throughput, schedule re-indexing during off-peak hours. Users query during business hours. The ingestion service indexes during nights and weekends. This separation prevents resource contention. If your organization operates globally, define off-peak by region or run ingestion on dedicated hardware. CPU fallback for embedding is viable if GPU is saturated. Modern sentence transformers run well on CPU. An AMD EPYC or Intel Xeon processor with many cores can embed hundreds of chunks per second. It's slower than GPU, but cheaper and more available. If your GPU is fully utilized by LLM inference, move embedding to CPU. The latency increase is acceptable for background indexing. Hardware scaling follows a simple pattern. Start with one GPU server handling everything. When LLM inference saturates the GPU, add a second GPU dedicated to serving. When embedding saturates, add CPU workers or a second GPU. When the vector database becomes a bottleneck, run Qdrant on its own server with fast SSDs and plenty of RAM. The architecture is horizontally modular. Each component can scale independently. Cost reality is worth stating. Local hardware has high upfront cost. A server with an NVIDIA A100, 64GB of RAM and fast storage might cost $15,000 or more. But the operating cost is predictable. Electricity, maintenance, occasional upgrades, there's no per-token pricing, there's no usage surprise. For an organization processing thousands of queries daily, the break-even point against cloud API costs often arrives within 12 to 18 months. The 2026 total cost of ownership analysis supports this directionally. Beyond certain usage thresholds, running open-source models on dedicated GPU servers becomes more cost-effective than per-token API fees. The exact threshold depends on your query volume, model size, and hardware choices. But the economics favor local deployment at scale. Let me walk you through a capacity planning example. Your organization has 50,000 SharePoint documents. They generate roughly 200,000 chunks. After chunking, each chunk is embedded into a 384-dimensional vector. The total vector storage is roughly 1 GB. With Qdrant overhead and metadata, call it 3 GB. This fits comfortably on a single server. Your users submit roughly 1,000 queries per day. Each query embeds the question, searches Qdrant, and calls LLAMA. Embedding takes 10 milliseconds. Qdrant search takes 50 milliseconds. LLM generation takes 3 seconds. Total latency is roughly 3.1 seconds per query. 1,000 queries per day is 42 queries per hour. Your GPU is idle most of the time. Now scale to 10,000 queries per day. That's 417 per hour, still manageable on a single GPU. But at 50,000 queries per day, you're processing 2,000 per hour during business hours. The GPU hits 80% utilization. Query latency degrades from 3 seconds to 6 seconds. Users notice. At this point, you add a second GPU server dedicated to LLM inference. You route queries round robin. Latency returns to 3 seconds. You have scaled horizontally. Vector database scaling follows a different curve. Search latency depends on vector count and index quality. 200,000 vectors search in under 100 milliseconds. 2 million vectors might take 200 milliseconds. 10 million might take half a second. If your document base grows to 1 million documents, consider sharding by department. The legal collection contains only legal documents. The HR collection contains only HR documents. The query interface routes based on the user's department or searches all collections in parallel. Each collection stays small and fast. Network bandwidth is rarely the bottleneck in local deployments. Your ingestion service talks to SharePoint over your corporate network. It talks to the vector database over the local LAN. The latency is milliseconds. The bandwidth is gigabits. The bottleneck is compute, not network. Focus your scaling budget on GPU and CPU, not on network switches. Storage scaling is predictable. Model weights don't grow unless you upgrade models. Vector storage grows with document count. Log storage grows with query volume. Plan for log rotation. Keep 30 days of detailed logs for troubleshooting. Archive older logs to cold storage. For a busy system, logs might consume hundreds of gigabytes per month. Don't let them fill your disk. Scaling isn't about buying bigger hardware. It's about understanding where the bottlenecks are and eliminating them systematically. Monitor everything, profile before optimizing, and scale one component at a time. This methodical approach prevents overspending on hardware you don't need while ensuring you never hit a wall you can't climb. Load testing validates your capacity assumptions before production deployment. Use a tool like Locust or K6 to simulate concurrent users. Start with 10 virtual users submitting queries every 30 seconds. Monitor latency and GPU utilization. Gradually increase to 50, then 100 users. Identify the breaking point. If the system degrades at 40 users, you know your single GPU setup handles 30 comfortably. Plan your hardware. So, your monitoring dashboard should show 4 main metrics at a glance. Query latency over the last hour with P50, P95, and P99 lines. GPU utilization percentage with a red threshold at 80%. Vector database query throughput in queries per second. And ingestion queue depth showing how many documents are waiting to be processed. These 4 metrics tell you whether your system is healthy, stressed, or failing. Everything else is detail you drill into when one of these 4 looks wrong. Alerting should be proactive, not reactive. Alert when P95 latency exceeds 5 seconds for 10 minutes. Alert when GPU utilization exceeds 80% for 15 minutes. Alert when ingestion queue depth exceeds 1,000 documents for 30 minutes. And alert when any component logs an error more than 10 times in 5 minutes. These alerts catch problems before users complain. Troubleshooting follows a simple decision tree. If query latency is high, check GPU utilization first. If the GPU is saturated, scale it. If the GPU is idle, check vector database latency. If QDRANT is slow, check index size and EF parameters. If QDRANT is fast, check the embedding model. If embedding is slow, check batch size and GPU memory. If everything is fast but the answer quality is poor, check chunking strategy and retrieval accuracy. Quality problems usually trace back to chunking. And here is the part that makes this future-proof. Modularity and model evolution. Llama 4 won't be the last open model. Next year there will be Llama 5, or a competitor with better reasoning, or a smaller model with equivalent performance. Your architecture must allow swapping models without rebuilding the pipeline. The RAG pattern is model agnostic. The vector database doesn't care which LLM generates the answer. The chunking logic doesn't care. The query interface doesn't care. They care about the prompt format and the API endpoint. Standardize on the Ollama API or an OpenAI-compatible local API like the one provided by VLLM or text generation inference. These APIs accept a model name, messages array, and parameters. When a new model arrives, you pull it, update the model name in your configuration, and restart the service. A/B testing is responsible model migration. Maintain a test suite of representative queries with expected answer characteristics. Run the old model and the new model against the same queries. Compare latency, accuracy, citation quality, and hallucination rate. Only promote the new model to production when it matches or exceeds the old model on your metrics. This prevents regressions. Embedding models also evolve. A new sentence transformer might offer better accuracy for your domain. But switching embedding models requires re-embedding your entire corpus. The old vectors and new vectors exist in different semantic spaces. You can't mix them. Plan this as a scheduled maintenance task. Build the new index in parallel. Validate it against a test query set. Then swap the collection names atomically. The downtime is seconds. Model quantization improves over time. A new quantization algorithm might reduce VRM usage with less quality loss. Re-quantize your existing model weights. Test the quantized model against your benchmark. If it passes, deploy. If it fails, keep the old quantization. This is continuous improvement, not big bang replacement. The Microsoft 365 ecosystem also evolves. SharePoint APIs change. Microsoft Graph adds new endpoints. Entra ID updates its authentication flows. Your ingestion service must handle API versioning. Use the API version parameter in SharePoint REST calls. Subscribe to Microsoft Graph change notifications where supported and monitor Microsoft's deprecation announcements. An ingestion service that breaks because an API changed isn't a technology failure. It's an operational failure. Modularity means each component has a well-defined interface. The ingestion service outputs text chunks with metadata. The chunking engine consumes text and outputs chunks. The embedding service consumes chunks and outputs vectors. The vector database consumes vectors and outputs search results. The LLM runtime consumes prompts and outputs text. The query interface consumes user input and orchestrates the rest. Change one component, the others stay the same. This is how you future-proof, not by predicting the future, but by building interfaces that don't care about the future. Let me talk about testing and continuous integration, because a production RAG system without tests is a liability waiting to happen. Your test suite should cover 3 layers. Unit tests for the chunking engine. Feed it a known document. Verify the chunks match with headings. Verify metadata is preserved. Verify chunk size stays within bounds. Integration tests for the ingestion pipeline. Point it at a test SharePoint library. Verify it authenticates, downloads, extracts, chunks, embeds, and stores correctly. End-to-end tests for the query flow. Submit a known question against a known document base. Verify the answer contains expected content. Verify citations, point to correct sources. Verify permission filtering excludes unauthorized content. Automate these tests in your CI pipeline. Run unit tests on every commit. Run integration tests on every pull request. Run end-to-end tests nightly against a staging environment that mirrors production. This catches regressions before they reach users. It gives you confidence to upgrade components, and it documents the expected behavior for new team members. Deployment patterns for this architecture are straightforward. The ingestion service, chunking engine, embedding model, and vector database are all containerized. You deploy them with Docker Compose for simple setups or Kubernetes for complex ones. The LLM runtime runs on bare metal or in a GPU-enabled container. The query interface is a standard web application deployed behind your corporate reverse proxy. Blue-green deployment minimizes downtime. You stand up a new version of the query interface alongside the old. You route 10% of traffic to the new version. You monitor error rates and latency. If metrics look good, you route 100%. If metrics degrade, you route back to the old version. This pattern works for the query interface, the ingestion service, and the vector database. It doesn't work for the LLM runtime if you only have one GPU. In that case, deploy during maintenance windows. Database migrations for Qdrant are minimal. Collections are created once. Vectors are inserted and updated by the ingestion service. You don't run schema migrations in the traditional sense. But if you change the embedding model, you must rebuild the collection, create a new collection with the new vector dimensions, re-index all documents into it, validate query accuracy against your test suite. Then atomically swap the collection names. The downtime is seconds. Model version control is worth implementing. Store model weights in a local artifact repository or on network-attached storage. Tag each model with version, quantization level, and deployment date. When you upgrade, keep the previous version available for rollback. A new model that performs worse on your test suite can be rolled back in minutes by pointing OLLAMA at the previous weights. Let us put this all together. The complete architecture blueprint. The full pipeline has 7 layers. Each layer runs inside your perimeter. Each layer has a specific job. And each layer connects to the next through a well-defined interface. Layer 1 is SharePoint Online or SharePoint on-premises. This is the storage tier. It holds your documents, enforces access controls, manages versions, and applies retention policies. It's the source of truth. Nothing in the AI layer overrides SharePoint governance. Layer 2 is the ingestion service. It authenticates via Microsoft Entra ID using OAuth 2.0. It enumerates document libraries using the SharePoint REST API or Microsoft Graph. It extracts text from Word documents, PDFs, Excel sheets, and PowerPoint decks. It detects changes using Delta Sync, and it outputs clean text chunks with structural metadata. Layer 3 is the chunking engine. It detects document type. It applies heading-aware chunking for Word, page-aware chunking for PDFs, row group chunking for Excel, slide level chunking for PowerPoint. It preserves metadata at every step: source URL, document title, author, last modified date, permission level. It outputs chunks ready for embedding. Layer 4 is the local embedding model. It runs a sentence transformer like all mini-LM L6v2 or BGE large N on your local GPU or CPU. It processes chunks in batches. It converts each chunk into a dense vector, and it outputs vectors with metadata payloads. Layer 5 is the vector database, Qdrant or V8, running on your local network via Docker. It stores vectors in a collection with HNSW indexing. It supports metadata filtering for permission-aware retrieval. It handles point updates for Delta Sync, and it returns the top K nearest neighbors in under 100 milliseconds. Layer 6 is the local Llama runtime. OLLAMA serving a quantized Llama 3 or Llama 4 model on your GPU server. It exposes a local REST API. It receives prompts containing system instructions, retrieve chunks, and user questions. It generates answers with low temperature for factual grounding, and it streams responses back to the query interface. Layer 7 is the query interface, a minimalist web application authenticated through Microsoft Entra ID. It embeds user questions. It queries the vector database with permission filtering. It constructs prompts. It calls OLAMA. It displays generated answers with clickable citations back to SharePoint documents. It logs every interaction, and it never exposes data to external APIs. That's the architecture. 7 layers. All local, all under your control. Now let me address common concerns. If the SharePoint API changes, your ingestion service uses versioned API calls. You test against preview versions in a staging environment. You migrate to new versions on your schedule, not Microsoft's. If the model hallucinates despite RAG, you lower the temperature. You tighten the system prompt. You add output validation in the query interface. You implement human feedback loops where users flag bad answers. And you monitor logs for patterns. Hallucination isn't eliminated, it's managed. If a user tries prompt injection, they craft a query designed to make the model ignore its instructions. You sanitize inputs, you enforce the system prompt at the API level, not just in the application. You validate that retrieved chunks match the query semantically before including them. And you log suspicious patterns. Prompt injection is an attack vector for any LLM system. Local deployment doesn't eliminate it, but it contains the blast radius to your perimeter. If hardware fails, you run qdrant with replication. You snapshot the vector index nightly, you keep model weights on network storage, and you document the recovery procedure. Local infrastructure requires operational discipline. The reward is control. If a user asks a question in German or French while your documents are in English, multilingual embedding models like multilingual E5 large handle this scenario. They map semantically equivalent sentences in different languages to nearby vectors. A user asking for Urlaubsrichtlinien in German retrieves the English vacation policy chunk because the embeddings are close in vector space. The LLM then generates the answer in the user's language. This isn't machine translation in the traditional sense. It's cross-lingual retrieval followed by monolingual generation. And it works surprisingly well with modern multilingual models. If a document contains a table that the extraction process fails to pass, the chunk contains garbled text. The embedding represents noise. When a user asks about the table content, the retrieval engine returns the noisy chunk. The LLM generates an answer based on partial or incorrect information. This is a data quality problem, not a model problem. The fix is better extraction, not better prompting. Invest in PDF table extractors like Camelot or TabulaPy. Test them on your actual document corpus. And fall back to manual review for documents that automated extraction can't handle. If the LLM refuses to answer a question because the system prompt is too restrictive, this happens when users ask about topics that are adjacent to sensitive areas. A user asks about employee benefits. The system prompt says only use provided context. The retrieved chunks contain benefits information, but the LLM interprets the question as potentially asking about other employees and refuses. This is over-refusal. The fix is to tune the system prompt carefully. Allow answers that are clearly supported by the context. Only refuse when the context genuinely doesn't contain the answer. And monitor refusal rates. A system that refuses 50% of queries isn't useful. If a document contains outdated information, a policy from 2024 might be superseded in 2025. Both versions exist in SharePoint because the old version is retained for legal reasons. The ingestion service indexes both. The retrieval engine returns both. The LLM synthesizes an answer that mixes old and new rules. This is a version control problem. The fix is metadata. Tag every chunk with effective date and superseded status. Filter out superseded documents at query time unless the user explicitly asks for historical versions. And train users to check the last modified date in citations. Let me walk through a complete query from start to finish so you see how the layers interact. Sarah, a project manager, opens the query interface. She types, "What is the approval process for vendor contracts over $50,000? The interface authenticates her via Entra ID and determines she belongs to the managers group, giving her a manager permission tier. The interface sends her question to the local embedding model. The model converts it into a 384-dimensional vector. The interface sends this vector to qdrant with a filter for permission tier less than or equal to manager. qdrant searches 200,000 vectors and returns the top 5 matches in 80 milliseconds. The matches include chunks from the procurement policy, the finance handbook, and the delegation of authority document. The interface constructs a prompt. System, you're a knowledgeable assistant that answers based on provided context. Use only the information in the context. Cite sources, context chunk 1 from procurement policy. docx, contracts exceeding $50,000 require procurement team review and CFO approval. Context chunk 2 from finance handbook. docx, vendor selection must follow the 3-bit process documented in section 4. Context chunk 3 from delegation of authority. docx, the CFO retains approval authority for all contracts above the departmental threshold. User question, what is the approval process for vendor contracts over $50,000? The interface sends this prompt to OLAMA running Llama 370BQ4. OLAMA generates the answer in 4 seconds. For vendor contracts over $50,000, the procurement team must first conduct a 3-bid process. The results are reviewed by procurement. Final approval requires the CFO as per the delegation of authority policy. Sources: procurement policy docx, finance handbook docx, delegation of authority docx. The interface displays the answer with clickable citations. Sarah clicks the procurement policy citation and opens the document in SharePoint. Total time from question to answer, 5 seconds. Total outbound data packets, 0. This isn't a theoretical architecture. It's a production pattern. 7 layers. Each layer has one job. Each layer passes structured data to the next. And the entire pipeline stays inside your perimeter. This architecture isn't a product you buy. It's a stance you take. The stance says your data is too useful to delegate. Your governance is too specific to outsource. And your AI capabilities should serve your perimeter, not someone else's. That's sovereign intelligence, not sovereign cloud. Sovereignty isn't about rejecting AI. It's about rejecting the assumption that intelligence must live in someone else's cloud. You now have the blueprint to turn your SharePoint into a private brain. Your data stays local, your model stays local, and your answers stay grounded in documents you already own. Share this with your security team. Follow for more architecture that respects your data.